Okay, moving right along. Post-hoc comparisons are, again, this is something I have to put it somewhere, so we're putting it here, right after analysis of variance. Okay, so you got a significant F. You did some science, you collected some data, you got 3 groups, let's say, or 4 groups, and you find, I got F is equal to 19. That's wow, and I look it up, or the SPSS tells me it's significant, but P is less than 0.01. Our null hypothesis was all the means were equal. Our alternative hypothesis, of course, is that 2 means different from each other, or that just this isn't true. It doesn't say which 2 means, though. So before you get excited and think, I'm going to publish this, and now I'll get a promotion and I'll get tenure. Perhaps I'll go into administration. Go over to the dark side for a while. Then I'll come back. But still, I'll always be tainted. Just playing. Which means it doesn't. The F doesn't tell you which means differ from each other. Damn. That's okay, by the way. The F, it's about a pattern in your data, and this is something that my old stats prof used to say. In Spence, the Scottish guy I've told you about, but it's also something. And Bill Tolving always said this too. So a couple smart people said this. It's like the post-hocs aren't important. It's what's the pattern in your data. Do you expect a uniform pattern? No. Do you expect a different pattern? And then you look at it and go, well, I see what's different. And I'm okay with that, frankly. Most people aren't. So which means differ from each other? Well, what you could do, you're thinking to yourself, you could do a t-test. So let's say you have 3 means. Group 1, group 2, group 3. So if we're going to do t-tests on all those means, we've got to go 1 versus 2, 2 versus, so 1 versus 2, 2 versus 3, and 1 versus 3. I think 3 t-tests. So it's doable. What you do is do something called the Bonferroni correction. Sounds delicious, doesn't it? Bonferroni? A little melted cheese on top. It's delicious. It's the San Francisco treat. That's obviously just for me, but I enjoyed it. 1 divided by 1 over n times alpha, and n is the number of corrections. This now tells you what your new alpha is. So we're going to do 3. So it's 1 divided by 3, so it's 1/3 times 0.05. So our new alpha level is going to be, because we don't want to change our alpha, because we start doing all these things, eventually we're going to find one by random chance alone. So our new alpha level is going to be 1/3 of 0.05. Okay? Our new critical value. And it's like, well, Dave, I don't have any t-tables that have that. Don't worry. There are, first of all, there are Bonferroni tables. But secondly, software will do it. No problem. The t-test, it's basically a t-test like this. One mean minus the other mean. It's called t prime. That's why there's a little delio there. That's a technical mathematical term. It's a delio. It's not. It's a prime. Square root of 2 times mean squared error divided by n. You're like, wait, what is that? Remember, mean squared error is just the variance. And if this was a t-test on the bottom, we would have, if it was just the variance, we'd have s squared 1 over n1 plus s squared 2 over n2. But they're the same value, mean squared error, so we're just going to do 2 times mean squared error. Yeah, that's all this is. This is just a t-test. It's very straightforward. You do this after you get the significant value. Okay? So that's one approach. Do you understand what just happened here? We've got a significant F. We have a value for a mean squared error. Done. You only do this, by the way, after you have a significant F. You can't do this, you don't get a significant F and go, well, try that. No. These all start out with the assumption that you add a significant F value for your meter. Or you can do this. That looks almost exactly the same. Except now it's not 2 times mean squared error, it's mean squared error. we have a new value called Q, which is an omniscient being. Star Trek reference. Thank you. So it's played by John Delancey. The largest mean minus the smallest mean. The larger mean minus the smaller mean, divided by, this time just square root of, you can square root over n, not 2 times, just 1. But that's just because of the way that this Q thing is distributed. And there are Q tables. It's probably on your back of your book. R is how many means do you have that you're comparing. So are you comparing 2 means, 3 means, 4 means, etc. And you know what? In all honesty, while I said about computers and let's have the, I actually my student usually, because I don't design experiments that have experiments as a rule. Typically, the stuff I do uses different kinds of stats. But when my students do these things and they bring me the ANOVA, I'll just do this with a calculator. I'll just do the post-hocs with a calculator because that's easy. I just read it and go done. But computer will do it. So Q with how many, and then the R, the subscript R is how many means are you comparing? Okay, that's called a studentized range. Then there's the Newman-Cool's test, or the student Newman-Cool's, because it uses the studentized range. This one looks a little different. What you do is you look up in a table, what's the value? Well, if this is the range, okay? The number of pairs. So, number of comparisons, like number of means. So if you have 4 groups, you have 4 means. That's what R is. Then 0.05, because you use 0.05 level of significance. The degrees of freedom for the error. So it's just degrees of freedom for mean squared error. And it gives you a value for Q. You look that up in a table. Then you multiply that times the square root of mean squared error over n. And it gives you this thing called W. It's like, what? W is actually a number. So let's say it gives you the number of 6 when you do this calculation. Then you see if any two means that differ by 6, they're significantly different. So it's a little bit different than what you're used to. The way this is usually shown actually in a computer kind of situation is that it'll just say by Newman-Cool's, or it might say student Newman-Cool's, or SNK. The following means are different. And it'll just show you. Nobody ever reports these values in papers. You never report the Q values, the W. You just don't. I don't know why, to be honest with you. It's just something that isn't done. I think it's probably because you're supposed to report your mean squared error, and anybody can then calculate it from it. But I've never understood why, but I remember the first paper I wrote all that stuff in. They were like, hey, you don't do that. That's not a thing that we do. What are you, a kid? Some kind of rookie? Yeah, sorry. Trying to be accurate. So it's any set of comparisons with range R. In other words, there's this many means between them. So if you're comparing, now this is an important point. Let's say you've got 6 groups, but only 4 of them interest you. Because a couple of them are just control groups that you threw and you don't care about. Now you're only comparing 4 means. Now R is only going to be 4. Okay? Well, let's say you only want to compare 2 groups. You've got 27 different control groups, like, classical conditioning experiments are like this sometimes. They've got like 15 control groups and 1 experimental group. All I want to do is say, look at and go, okay, I can see all the control groups are the same. I'll pick the regular old control group and I'll compare that to the experimental group. Okay? So that, in that case, you're going to range 2. Okay? So it depends on whatever the hell it is you're comparing. There's also a test called Tukey's test, Tukey's HSD. HSD stands for, and I kid you not, honestly significantly different. It just always uses the largest range. So what it does is says, I don't care if you're comparing 2, but if you have 27 groups, you put 27 in. It's a little more conservative. Yeah. There's also a test called the LSD. There really is, and it means least significant difference. Okay. And I'm sure that was developed during the 60s for fun. I'm sure there was a bunch of statisticians going, if we could name something after LSD, that would be great. Which comparison of these, and I've picked 3 or 4 popular ones. There are a zillion of them. Zillion is a little strong, but there's tens of them. Okay? You know what most people do? They do all of them and then report the ones that worked. You shouldn't do that. It's called p-hacking, and you just shouldn't do shit like that. It's just unethical. It's scientifically unethical. I don't like that very much. It's like when you're when you think you have something, well, let's keep testing subjects until we find the difference. Don't do that. That's what gives science a bad name. Don't go out giving science a bad name. Piss me off. And I'll find it. I'd stick to one in a paper. It's hard to explain to an editor or a referee or a prof who's marking your paper, your honors thesis, why you used Newman-Cool's in this experiment, in this analysis, and then the next paragraph of your results say, oh, well, I decided now to switch over to something else. Just to mix it up a little. No one's going to accept that as a reason. I've used, when I have done analysis variance stuff, I've used HSV. It's a nice compromise between being conservative enough so it doesn't give a lot of false positives, but it finds things that are there. So that's what I've used. And that's probably the most common one you see, is the HSV. But you can use any of them. I would just stick to one type of analysis in any given paper, that's all. Just I would never ask you ever to do one of these by hand because people don't. They tend to click buttons. When I showed you the SPSS thing, analysis of variance, and I can show you right after we finish recording here, and just do it again, you can just click comparisons, and it just does them. It's literally, it's under options, I think. And it's literally just sitting there and you can do them. Questions?